To build an effective computer vision project, you have to know exactly how to navigate the baseline architectures. By mapping out exactly how the essential convolutional neural networks are structured, we can systematically choose the optimal model for any specific task. Every new architecture starts at the exact same testing ground, the ImageNet dataset. With 1.2 million images spread across 1,000 distinct categories, it serves as the universal benchmark for image classification. ImageNet tests for broad variety, but it also measures fine-grained classification. The dataset includes nearly 100 different breeds of dogs, forcing algorithms to detect incredibly subtle differences within a single overall class. When researchers train a new model on ImageNet, they publish their results and share the trained model weights. Through transfer learning, these massive, highly optimized weight matrices can be downloaded and used as the starting point for your own custom projects. Utilizing those pre-trained weights bypasses weeks of initial training time. It takes enterprise-grade computational structures and makes them practical for everyday local deployment. Modern image classification is built on a specific structural foundation established in 2012. That year, a model called AlexNet outperformed classical computer vision techniques by an 11% margin, proving deep learning was the viable path forward. AlexNet defined the convolutional block. A 227-pixel input image is processed by an 11 by 11 filter. The filter sweeps the data, downscaling to a compressed 6 by 6 feature map. This output is flattened into 3 dense layers, which act as the learning algorithm calculating final probabilities. This massive architecture contained 60 million parameters. In 2012, no single GPU had the memory to hold it all, forcing researchers to split the network across 2 separate graphics cards. AlexNet permanently set the blueprint: use convolutional blocks to extract the visual features, and follow them with dense, fully connected layers to execute the classification. 2 years later, the VGG architecture tested a direct hypothesis. What happens if you heavily increase the network's depth? VGG expanded the model from AlexNet's 5 layers to 16 and eventually 19 layers. To make a deeper network computationally feasible, VGG replaced the massive 11 by 11 filter with a sequential stack of smaller 3 by 3 filters. This significantly drops the overall parameter count, which guards against the model memorizing training data and lowers the risk of overfitting. VGG demonstrated that deep sequences of small filters create a more efficient and adaptable feature extractor than a single large filter. Pushing depth further introduces a severe hardware bottleneck. Stacking layer after layer exponentially increases the raw computations required to process an image. GoogLeNet bypassed this limit with the Inception block. Instead of passing data sequentially, it splits the stream into parallel paths, applying filters simultaneously. To manage the workload, one-by-one convolutions act as bottlenecks, constricting incoming data volume right before it enters the more expensive, larger convolutions. Because the network was incredibly deep, researchers inserted classification layers at intermediate steps. This ensured the network maintained a strong loss signal at multiple levels during early stages of training. The Inception block decoupled network depth from computational cost, producing a highly complex architecture that required significantly less processing power to run. As researchers pushed past 22 layers, networks hit a mathematical wall. The models stopped improving. This was caused by the vanishing gradient problem. During training, the error gradient backpropagates from the network's end. In deep networks, this gradient shrinks and vanishes before adjusting initial layers. ResNet solved this with the skip connection, allowing the signal to bypass layer blocks entirely, pushing a clear signal forward without distortion. Bypassing the vanishing gradient allowed ResNet to scale up to an incredible 152 layers, achieving an accuracy rate that officially surpassed human performance on the ImageNet benchmark. By removing the structural limits of depth, ResNet established itself as the universal baseline for modern image recognition. When deploying a model today, an architecture with a massive parameter count does not automatically guarantee better accuracy for your specific use case. This scatterplot maps architecture performance. The x-axis tracks computations, the y-axis tracks accuracy, and bubble size represents parameter count. The top left quadrant is optimal for high accuracy and low computations, ideal for mobile apps, while massive top right models are reserved for dedicated servers. Model selection requires matching the architectural footprint directly to your specific deployment constraints. Attempting to train any of these foundational architectures from scratch on your own dataset is a massive waste of computational resources. The practical implementation is fine-tuning. You keep the bulk of the pre-trained ImageNet architecture completely intact, acting as an off-the-shelf feature extractor. You only detach and replace the final classification layers to target the specific categories of your project. If standard fine-tuning isn't enough, advanced techniques like neural architecture search use algorithms to automatically construct highly specialized custom network blocks for difficult edge cases. By understanding the structural logic of VGG, GoogLeNet, and ResNet, you can download their pre-trained weights, swap the final layers, and deploy state-of-the-art computer vision models in a fraction of the time.